Welcome back, everybody. And now we are in Unit 2. This unit, the two sections we're going to cover in your text are sections 1.2 and 1.3. The topics covered there are functions, graphs, slope, and some applications as well. As always, the goal of my pre-recorded lecture is to give you an overview of all the topics and show you at least an example of each type. That's my goal. But I don't have time to cover every single example in the text. And also a lot of times I do create my own examples as well. So I still strongly encourage you to read through your text and also use your text resources. So there's lots of video resources available with your text as well, and things like animation and PowerPoints there too. But I think the additional videos are really helpful if you find you need more than just these pre-recorded lectures. I try to keep the pre-recorded lectures to around an hour or so. So they're not meant to be, a full week's lecture material, but hopefully they'll get you started and give you a good introduction to what we're learning each week. So the first thing we're going to talk about is functions. And before we get there, there's one definition first, and that's the idea of a relation or relationship. So when we have two sets of data, they may have a relationship together. For our purposes, most times when we're looking at data, they do have a relationship. We kind of skip that beginning piece. But with real world data, in the beginning, the first thing we look at is for patterns. So is there really a pattern between these two variables? Is there some sort of relationship? You can see patterns or relationships between data in different ways. So one way is a graph. Another way is a table or with a set of points. And a third way is with an equation. So if you have a graph, or you have a table or an equation, for instance, then you definitely have a relationship there, right? You're looking at that data and you're seeing the relationship, right? Either in an equation form or in a graph form or as a set of points. Now, in a relation, the first part of the data is called the domain, and those are usually your X values if you're using X and Y data. The second set is called the range, and again, these are usually the Y values. If you're using different variables, then it would be, the first and second coordinates appropriately, but for most cases, we're using X's and Y's. So most people think of the domain as a set of all X values and the range as a set of all Y values. So in our first example here, we're just going to practice finding the domain and range. And these are relations, and relation just means that there's some sort of relationship between the two data points, whatever it may be. So here I have a set of points. And this example would also work if you had a table of data as well. So you just sort of have a table or a set of points. You could pick up the domain and range very quickly. Again, domain would be your X values and range would be your Y values. So think about your sets of points. When you have a set of points, your X value always comes first and your Y value is always second. So domain is first and the range is second as well. I always think of it because of alphabetical order, right? D comes before R, X comes before Y. So that's an easy way to remember it. So for our domain here, we can write it as D, and it is a set of points. So I'm going to use these little squiggly brackets here, curly brackets, and I'm just going to pick out my X values. So 1, -7, 0, and 15. For the range, we're going to go ahead and pick out the Y values. So range is R. And again, they would be 3, the 8, -4, and the 2. Now, in a set of points, they do not have to be in order. So notice here how I did not put the numbers in order. I think most of the times you will see the numbers written in order, but if they're not, it's not incorrect. It's perfectly fine. The only thing that we do not do in sets is repeat values. So if for some reason, let's say the second point was -7, 3, so you have the 3 again, you only need to write it one time. Otherwise, the order doesn't matter. So there's our domain and range. So if you have a finite set like this, it's pretty easy to pick out. In our next example, we have an equation. Now, equations are actually a little bit more difficult. You kind of have to think ahead and think about, okay, what's going on here with this equation? And we'll see later on in the lecture and the lectures over the coming units that there are certain things to look for in equations. But for now, I'm just going to talk generally. So you want to think about what x values are relevant and what y values are relevant for this equation. So for the x values, again, that's your domain. Think about, okay, well, what x values could I plug in here and actually get an answer? For instance, if I plug in something like x equals 0, that would be y equals 2 times 0 minus 3, which is just -3. So I can plug in 0, I can get an answer. Could I plug in something different? Can I plug in 100? Right? If I think about this, yeah, I could plug in 100, right? I could do 2 times 100 is 200, minus 3 is 197. I could plug in 1,000. I could plug in 10,000, right? I could kind of make the number as big as I want to. I could plug in negatives, right? I could plug in -10, right? Y equals 2 times -10 minus 3. Well, that's -20 minus 3 is -23. Again, I could plug in -15, -500, -5 million. So if I think about this equation here, I can really plug in any number I want, right? Because I could always multiply it by 2 and then subtract 3. There's nothing weird that would happen there. So because I can plug in any x value that I want, our domain in that case is what we call all real numbers. And we write that often using interval notation, and I'll talk more about that in a little bit. And we would write that as -infinity to infinity. So this squiggly symbol here is infinity. It means it goes on forever. So these go on to the negatives forever, those go on to the positives forever. Now, if you think about your range here, and sometimes a graph helps, right? If I look at this equation, it's just linear, right? There's no squares, there's no cubes, there's nothing weird going on here. So if I think about our points, I'm at 0, -3, which is about right here, -10, -23, again, maybe about right here, 100, 197, maybe about right here. I'm just estimating. But, I get a graph that looks something like this. And you can see that the graph is going to keep going up, and it's going to keep going down in this direction. So theoretically, it should also encompass all the y values as well, right? I'm not skipping over any y values or anything like that. So our range here is also all real numbers, or -infinity to infinity. Now our last example here is an equation. Not an equation, is a graph, excuse me. And I really like graphs. So I like graphs as well, and I think they're also helpful with equations too. So you can notice here I did do a graph anyway. So this is where technology can help. If you're getting stuck on equations, you're like, I can't really figure out which values would be relevant, try graphing it and seeing what the picture does, and that helps too. So here I have a graph. This will keep continuing in both directions if you didn't know that. So it would keep going. And again, I want to think about domain and range here. So remember, your domain would be your x values. So you're just thinking about your x values here. And if you remember your graph, your x values is on the horizontal axis. So they run in a left to right direction. So when you're thinking about domain and range, I want you to think about just one direction at a time, not try to do both at once. So domain is x's, just x's. So I'm just thinking, okay, what's happening left to right on that graph? So if I follow my graph here and I just kind of follow the line, I can see that, it would keep going forever, right? And it does keep moving to the right, slowly, but it keeps moving to the right. And over here, if I follow this graph, I can see that, it would keep going left forever, slowly, but it does keep going. So I'm going to run through all the x values. So my domain again here is all real numbers. My range, though, is not all real numbers, and that's why I like this example. So remember, range are your y values, and y values run up and down. So if you follow your graph again, if I follow my graph, I can see that the arrows are pointing upward, right? So this graph is going to keep going up forever. And on the y-axis, going up means the positive values. But when I try to come back down and follow along this curve, what happens is I get to this point here, and then I turn around and go back up. So there is a lowest point right here, right? We're never going to go below that spot. Well, that y value is at -1, -2, -3. So our range is not all real numbers. It goes positive forever, but it doesn't go negative forever. It stops at -3. So we could say that our y values are greater than or equal to -3. This right here is a version of set notation. It's kind of a lazy version, doesn't have the full set symbols, but we see that often. Or interval notation, it would look like this, -3, infinity. And I'm going to take a second right now and talk about interval notation. Now, in interval notation, there's a few things that you do need to note. So first of all, with interval notation, we always write the smallest number first, and then comma and the larger number. So you always go small to large. So that's why here I have the negative on the left and the infinity on the right. Now, the infinity is positive. Positive numbers are always bigger than negative numbers, even though infinity is not really a number. So I always go small to large. The other thing is that we use brackets when the idea is a less than or equal to or greater than or equal to. So when the end point is included. So here, right, that graph actually touches the -3, right? It goes down to -3. It's not like a hole there or a jump or anything. It physically touches it. So that endpoint is included. That's why I use a bracket there. We use parentheses when the idea is strict less than or greater than. So your endpoint is not included. So we would see that, for instance, if there was a hole in the graph there. So if you're physically skipping over it, we're going to see graphs later on that use this where there may be breaks in the graph, so we never actually touch the value, and you'd use a parenthesis there. We do also use parentheses for infinities. So if you can mix and match the symbols, it doesn't matter, but you would also use a parenthesis for infinity because we can never really quite reach infinity, right? We can never touch it. So we use a parenthesis there. I'm going to add in just one more example here, just so you can see some that don't have infinities all the time. And I'm just going to make this up. It's not going to be symmetric, but you can kind of bear with me. Let's say we kind of have like an oval shape. So maybe it comes down here to -5. It goes up to 2 on the x-axis. Maybe its height is 1, and then this height is -2. Okay. And again, I want to find domain and range. So for your domain, it's just the x values. So you're looking in a left to right direction. So if I follow this curve, the farthest it goes left is -5, right? And then it goes up and around, and then the farthest it goes right is 2, and then it starts looping back around again. So all of those values for the domain are between -5 and 2. Now there's no holes in the middle, right? It goes through all of them. And we actually do touch the -5 and the 2. So I'm going to use brackets there because we do actually touch those values. For my range, again, you're just thinking in an up and down direction, right? So it goes up to 1, it goes down to -2. It never goes beyond those values. So again, go from smaller number to bigger number. So -2 is smaller than 1. And then again, it touches those values. So I would use brackets there. You can also write it like this. So you could write it as -5 is less than or equal to x is less than or equal to 2. Or -2 is less than or equal to y is less than or equal to 1. That is also correct. So this would be in set notation. This would be interval notation. It is important to know the difference. A lot of times they will be specific in homework questions on which kind of notation you should use. We do use interval notation a lot. It does look like points. So you just want to be a little careful there when you're reading it to make sure, you know, if you're looking at a point or you're looking at an interval. So that's something to watch out for. Now we've talked about relations, just any sort of relationship in particular, but functions are a certain kind of relation, so a very specific kind of relation. And that happens in which the domain corresponds to or each element in the domain corresponds to exactly one element in the range. It's much easier to tell when something is not a function. So for instance, something is not a function if the same x value has 2 different y values. So for instance, let's say the x value 2 had both the y value 3 and the y value 4, right? So maybe your graph has the points 2, 3, and also the 0.24. Something like this is not a function. Now, these things do exist. So don't get confused with, does it not exist or something like that. These are perfectly good examples of relationships and relations in math. There's lots of examples that are not functions that we use all the time. Circles, for instance, are not functions. Neither are ovals. And of course, these are really important shapes, right? So not everything is a function. It just makes life a little bit easier when we have functions because we know that for each x, there's only one output. So you're not, confused like, oh, is the answer 3 or is it 4? I don't know, right? There's only one answer. So it makes things a little bit easier. As a real life example, something that is not a function would be like the sale of a diamond ring or, any sort of expensive jewelry. A 1 carat, for instance, diamond ring could have very different prices depending on the quality of the stone, right? And even the shop and things like that. So maybe a 1 carat, I don't know, square cut stone here is $1,000, but over there it's 500, and then here it's 5,000, right? So it can vary, even though they're all buying 1 carat. So that's not a function. You have different prices for the same input of 1 carat. Something like a Girl Scout cookie, at least last I checked, they were each $5 per box. Didn't matter the flavor or anything like that. It didn't matter how many boxes you bought. It was just 1 box of cookies is $5. 2 boxes, $10. So there's no change there. Each input is always the same price. So that would be a function in the real world. So let's look at a couple of examples here and see if we can determine if we do or do not have functions now. So these are all relations. Anytime you have some coordination of points, graphs, equations, you have a relationship. So now we're just determining, is it also a function? Is it a special kind of relation that's a function? So what I'm going to do here is I'm going to look to basically to see if those x values are being repeated. So if I look here, I have the x value of 1, 3, 5, and 7. I don't have any repeats. Each x value is unique and has only one output. So this is perfectly fine. This is a function. If I look at my second example, again, I'm looking at the x values. I have -7, 3, 1, and 0. There's no issue there. The x values are not repeated. Now, I know you're saying, wait, but I see lots of zeros. That's true. But the value of x is 0 only appears once. These are values of y is 0. For a function, I don't care if the y repeats. There are different definitions. So a stronger definition of a function is called a one-to-one function, in which case neither x or y repeat. But we're not looking at that here. We're just looking at functions. So you're looking for, does the x value repeat, right? So if you have the same x going to different y's, then that is not a function. So that's what I'm looking for here. And I don't have that, right? I have different x's. And then even though the x is 0 and the y repeats, I don't care. So each x has its own y. If I look at my last example, here's where we see a problem. Notice how when you have x is 1, you have one answer of 5 and a different answer of 4. So here you have the same x value going to 2 different y values. So that's where we have not a function.